All right, folks, let's dive into the heart of manufacturing welding. This field where precision and consistency are crucial has always been juggling with the high temperatures and currents. That's why we turn to our trusty robotics companion to tackle this challenge. Hi, I am Saad Jamil from National University of Sciences and Technology, Pakistan, accompanied by Mr. Mughira Salim from NUST, the same university as mine, Etizaz Hassan from Air University, Pakistan, guided by our mentor Zishan Khan from King Fahad University of Petroleum and Minerals, Saudi Arabia. We are here to present our project design and fabrication of a 6D DOF gantry robot for welding application. This project is pushing the boundaries of safety, precision, and efficiency in welding. So let's get into the detail and see how this innovation is setting new standards in the industry. All right, let's break down to the cool stuff. We will first discuss the main idea, the problem statement of this research. Then, with a glimpse of little introduction and work that has been done till now, we will jump to the design of our Gantry robot and its mathematical modeling, which includes poses, joints, and velocity calculation. Before doing the hardware selection and final manufacturing, it was very important to do stress analysis. Then, I will conclude my presentation by providing some guidance on future direction and potential research areas. This work aims to build a robot that has 6 degrees of freedom so that it can cater all the possible position in its workspace. To achieve 6 degrees of freedom, a 4DF manipulator that is green and a 2 degree of freedom gantry is made, this black part here in the image. The gantry can move in X and Y direction parallel to the floor. It is modeled separately. These two joints are prismatic. The manipulator has four revolute joints. The model was first created and simulated in MATLAB environment to calculate joint and effector pose and velocity. Once simulation and safety checks are complete, we integrate it with hardware. After physical model works perfectly, we conducted tests for precision, robustness, and safety. Mostly industrial robots have fixed bases. They are called manipulators and are used for handling objects in the environment. Manipulators are highly customizable, meaning that one manipulator can be programmed to do several tasks. This level of adaptability made a new revolution called Industry 4.0 and 5.0. Briefly, Industry 4.0 refers to the integration of smart technologies and automation in the manufacturing, and Industry 5.0 is the collaborative relationship between human and advanced technologies. In addition to the fixed based robots, the industry also incorporates movable robots such as gantry system. A gantry function as a horizontal bridge facilitates movement within a plane. It is important to note that although these gantry robots have some mobility, they are not as freely mobile as a robotic car. Their movement is confined to a specific area. The manipulator and effector is a rotatable welding head, which is equipped with some fuses for temperature and current safety. So robots have proved both efficient and safe. So an enormous number of industries have been employing them for many different, difficult, and repeated tasks. Industrial robots have broadly been classified into types. This is the Da Vinci robot, which is a parallel robot. The end effector is connected to the parallel links. This is the most common robot, which is the serial link robot. Each link is connected to the other link serially in a chain fashion. And this has been and industries have this have been used in industries for application like welding, carpenting, and simple object manipulation like pick and place. I think most of us have at least know what a CNC machine is. A CNC machine is used for precise material machining for designing metal parts. CNC machine is basically a type of gantry robot. Our end product is the fusion of two, the gantry and a manipulator. which is actually very beneficial over the standard manipulator. This is mainly because of the obviously because of the Gantry. Some researchers have shown that these gantry robots are able to work in the large structures like shipyards. With their ability to work in the large structures, here comes the most important aspect of the robotics, that either robot consume less power and follow the optimal path to reach the goal post. Mr. Yang, in a survey of welding robot intelligent path optimization, has answered this question. Alongside Wang, the optimal real time path planning of the Gantry robot for the high precision is also discussed by the section in his proceedings of multi-domain design assessment for aerospace components. After reviewing the latest research in Gantry robot, let us dive into our contribution for this research. Here is a block diagram of our controller. I have stated in the introduction that our Gantry robot is a 6 degree of freedom, which clearly means that it has 6 joints, with each has one motor, so a total of 6 motors. The main control scheme is the feedback control, and position is the signal that is fed back to the controller. Here, notice one important factor that we have two separate control scheme, one for the gantry and one for the manipulator. First, gantry moves the manipulator close to the object, then it come into action for the desired pose. Here, MATLAB is responsible for calculation of desired pose by using inverse kinematics. I will explain inverse kinematics in future slides, which gives the joint angle. Basically, the inverse kinematics is responsible for the joint angles. These joint angles are then fed to the microcontroller for further action. Gantry has linear movement in x and y. Oh, where is my pointer? Sorry. Gantry has linear movement in x and y direction. Gantry controllers control two stepper motors which are connected to the lead screw that converts rotatory motion to the linear motion. First, gantry controller translates the manipulator to the desired position as discussed in the previous slide. Then manipulator controllers comes into action. The diagram here is the CAD model of our gantry system, which then fabricated. Robot moves 900 millimeter in X direction and 300 millimeter in Y direction. After the gantry system, the complex but very common part is the manufacturing of manipulator. It has 4 degree of freedom, with each has a DC servo motor. The control scheme is literally the same as of gantry system, that it uses the position feedback and error is minimized between the current position and the desired set point. The manufacturing procedure is also the same as of the gantry system. First, the CAD modeling is done with the parameters shown here. Then it is fabricated into the actual metal hardware. I will discuss the hardware selection in the later part, where the hardware material and the motor selection is discussed in detail. Till here, a sketch of a robot has completed, and now we will dive into the most important and the crucial part, the mathematical modeling. A mathematical representation of our model has some independent variable. In our case, we have joint angle, and some dependent variable, the pose of the end effector. Here are some other parameters. These are constants like the robot link parameters. See the schematic diagram here. Uh, Focus on the frame 0. Look, this joint is oriented in an upward direction, whereas the frame 1 is oriented in the outward direction. Okay, now the main question, how to organize all the system parameters into a matrix or an equation? The scientists Denevit and Hartenberg have the solution. We will calculate these parameters which end up in an equation that is for the forward and inverse kinematics. I will explain them in detail in the next slides. So right now we just need to focus on what else we can get. Forward kinematics equation has basically the position. So with the first derivative of the position, we can calculate the velocity of our system, and also we will calculate the force propagation. The DH table basically takes care all the parameters of the link. It comprises of link length, that is alpha I minus 1, link twist, which is the angle between two adjacent links, DI is the joint offset, and theta I is the joint angle. After analyzing the robot geometry, this DH table is prepared for six parameters. Let me give a little more insight that how we calculated these parameters. First, we have made the frame assignment where z-axis are aligned with the joint axis of all the lengths. Then x-axis are drawn where two consecutive z-axes are intersecting. The x-axis is then the perpendicular to the plane of both the z-axis. Otherwise, x-axis is in the direction of the link. This I basically represents the joint number. Each parameter is referenced with the consecutive previous joint. The first parameter is referenced with the global frame that is mostly the same as the first frame. After DH table, we have found the link transformation. It is a combination of the four DH parameters: the link length, the rotation of the link, then the joint offset, and lastly the joint and the rotation of the joint, which calculates to the equation number 1. This is called the transformation for the single link. After finding each link transformation, then we calculated the transformation between the gantry frame and the end effector frame. So we calculate this by simply multiplying with each transformation. This is called the forward kinematics. Again, focusing on the equation number 1, the parameter provided here are joint configuration, which results in the link pose that contain the rotation matrix and the translation vector. This last column is basically the translation vector. The forward kinematics is the calculation of end effector pose given the joint coordinate. But what we actually know is the point where the object should weld. And from that point, we need to find out the joint coordinate that result in reaching that point. This concept is called inverse kinematics. We have mainly two methods for calculation of inverse kinematics. One is the analytical method and other is the graphical method. Graphical method is perfect for solving a smaller and non-redundant manipulator, which gives closed form solution with easy to use techniques, and let us see how it is done. From the top view, we can find the theta 1 by using the right angle triangle calculation. Now focus on the side view where we have a triangle shown in red using the law of cosine to find out the value of phi 1 and phi 3. Phi 2 is calculated by the right angle triangle approach. Theta 2 is simply the difference of phi 2 from phi 1, and theta 3 is the difference of pi from phi 3. Till now we got theta 1, theta 2 and theta 3. Theta 4 is only for the orientation of the end effector, which calculates with this formula from the forward kinematics. Now the pose and joint coordinates have calculated. Now we move to the velocity calculation. For velocity calculation, we use velocity propagation method. In velocity propagation, the velocity of previous joint is reflected into the velocity of the next joint. And angular velocity is responsible for both angular velocities and linear velocities. Let us focus on the angular velocity, which is the sum of the angular velocity of the previous joint seen through the current frame. That is why we have multiplied it with the rotation matrix and the velocity of the current joint. After a lot of calculation and hassle and joint transformation, we finally were able to move the robot in the simulation. This is the robot in simulation. We have used Peter Code Robotics Toolbox in MATLAB for simulation. For Gantry, we have made two prismatic joints, and here is the workspace of the manipulator. This workspace is only for one gantry position. And if this goes on forever, it can calculate the complete workspace of the robot. After perfect results in simulation, all the joint limits were calculated so as to implement it on the hardware. Selection of hardware is another crucial part in hardware implementation. Before going towards motor selection part, first it is important to select the material of the lens. We have selected aluminum because of its availability and affordability. So the robot parts were CAD modeled using the SolidWorks platform. Then we did stress analysis on the link plate. The factor of safety is 8.9 for 1.5 kilogram of weight. Then for the gantry supporting rod, the factor of safety of 3.8 is achieved since it has to support a 15 kg of weight. Aluminum is selected as the material for the link after the stress analysis. Then the next part is the selection of the motor. We had to use the worst case scenarios. So if anything bad happened to the robot, it should be able to stabilize and handle the worst cases. So torques were calculated on each joint that depends on the weight and inertia of the link and also the center of mass distance from the motor. Here is the selection of the elbow motor. uh, the torque at the elbow is given with this equation. After solving that, the torque at the elbow is 1.85 Newton meter. So 2.5 Newton meter torque motor is selected for this joint. The same calculation is done for the shoulder and base motor. After the manipulator motors, we then selected gantry motors. Gantry is operated by a stepper motor which is connected with the lead screw. The formula for the torque of the lead screw is this. These are the parameters for the lead screw frictional forces. After calculation, 2.59 Newton millimeter is the torque. To control the motors, Arduino Mega was used. Reason for selecting Arduino Mega was it has to terminate 4 DC servo motors and 2 stepper motors, along with the safety gears of the robot. And it is very efficient in data processing and it is very accurate. Now the last thing was to write the Arduino code for the robot. Robot algorithm was break into two parts. One is the MATLAB side and another is the microcontroller side. In microcontroller side, input is the joint position from the MATLAB. First, gantry control starts to move the manipulator to the desired pose. As the gantry reaches its desired position, then manipulator control starts and move the manipulator to the desired position with again the continuous feedback on the position. Now the question left is how the MATLAB generates the joint angle. It is a simpler calculation of inverse kinematics which gives the joint coordinates. It then fed to the microcontroller. In last, this robot can effectively utilized in Industry 4.0 in the facilitation of combined tasks between robots and humans. There are some unattainable poses that robot cannot achieve either because of its manufacturing or a weaker control. These poses were identified by mathematical modeling. The future direction for this project is it does not have dynamic control embedded. So the joint coordinates that were calculated from inverse kinematics will then fed to the dynamics model that find out the torques required to reach that point. And this can give the optimal trajectory for achieving a pose. And last, a simple rod design can be updated to the reel of feed rod and roller mechanism for better positioning of welding head over the workpiece. All right, these are the references for our presentation. Thank you everyone for your time and interest in the presentation. If you have any question, feel free to ask.